Across the world, cities have been implementing bike-sharing systems in an attempt to reduce residents' dependence on cars and other vehicles, and provide easy access to transportation to those that don't own a car for themselves. The idea of a bike-sharing system is simple yet impactful. Reduced use of cars means less traffic and fewer fossil fuels entering the atmosphere. Easy access transportation is provided to every citizen who can ride a bike, and deliveries in which traditional transportation methods are infeasible can be simplified. However, large-scale implementations of these ideas don't always go smoothly. In fact, many of the problems with bike-sharing systems only become apparent after cities invest in a large network of public-use bikes. Many citizens who can benefit from such a system often live too far away from a bike-share hub to be feasibly used. Additionally, those who do end up riding these bikes will deposit them at the end of the day at a hub that is too full, leaving others around the city empty. The city then has to collect and redistribute the bikes regularly. In China, the situation got so bad that the thousands of systems the government invested in were hardly used, leading to huge plots of land filled with rusting and neglected bikes. To solve these problems and many more along the way, we would like to introduce Team Autocycle. We will show you that the self-balancing, self-driving bike that we are developing can help create a greener, more connected world.
Our team's main deliverable for this project is a prototype of the self-balancing, self-driving Autocycle. Let's see how we're building it. Our team decided to begin research by developing realistic mathematical simulations of our major systems. Such simulations allow us to design our control system theoretically, and will allow us to compare our experimental results to what was predicted. We also spec sensors and actuators based on the simulated results. Two main simulations were created: a dynamical model of the bike chassis responding to disturbances and control torques, and a top-down path planning simulation. The dynamical model was developed based on linearized equations of bicycle motion derived from the existing literature. Using these, we can effectively predict how our bicycle will tilt and turn, giving starting conditions and control signals. Our simulation was expanded to include both uncontrolled and controlled dynamics, in which we tested out several different control algorithms to compare and determine which one suited our needs best.
For the navigation section, we implemented an object classification system capable of detecting and labeling a variety of items in front of the bicycle. Being able to detect what kind of object is in the view would allow the bicycle to be able to react differently to different kinds of objects, such as a stop sign or a traffic cone. We also use a LiDAR system to calculate the distance from detected objects. Together, these streams of data describe the obstacles that the bicycle will have to avoid. We have developed a path planning algorithm that utilizes this data along with Bezier curves in order to plot out paths around the obstacles for the bike to follow in real time.
The Autocycle prototype is controlled by an Arduino Due with a Raspberry Pi acting between it and a Coral board, which will run the navigation code. It communicates using a mixture of commercially available connectors, such as Ethernet cables, USB cables, and CAN cables, with some of the shorter connections made by standard wires. The Autocycle prototype is manipulated by two motors, one mounted axially on the bike's drive gear to control the bike's speed, and the other mounted to the front handlebars by a drive pulley to control the bike's heading. Component parts needed to attach the onboard electronics, motors, and drive pulley were purchased and machined here at the University of Maryland in the Instructional Fabrication Lab.
Custom components were designed through a long process of design iteration. The handlebar motor we selected required custom-fit housing to mount onto the frame of the Autocycle prototype. Some store-bought parts required serious modifications to get them to fix the prototype's chassis, like the addition of threaded holes or an increase in the part's internal diameter by way of machining. Custom parts needed to be tested and redesigned to make sure that the parts fit securely into their intended spots. Early parts were printed out of PLA on privately owned 3D printers, with our current prototype's components printed out of nylon or machined from steel. A Schwinn Cosgrove cruiser bicycle serves the chassis for our prototype, which has been outfitted with custom components and sensors needed to achieve stabilization and navigation. An Arduino Due microcontroller is given positional data through an inertial measurement unit and controls the front torque motor. Through a system of belts and pulleys, the handlebars of the bike can be turned to the correct orientation needed to achieve stability, or to turn to the left or the right. When out of autonomous mode, the motor is shut off, allowing the human rider to ride the bike easily.
The end goal for our research is to have a fully functioning, self-driving, and self-balancing electric bike. We hope that our project will be able to drive itself, with supervision of course, from Ellicott Hall to A. James Clark Hall.
As with all Gemstone teams, the overall goal of our project is to do good.
Team Autocycle plans to do this by improving transportation infrastructure and by overall reducing the global carbon footprint. We hope that our research into developing a self-stabilizing bicycle will pave the way for future research and development of large-scale autonomous bike-sharing services. By allowing the bicycles on a bike share to return to convenient locations, or allowing a user to summon a bike on demand, we hope to expand the effectiveness and user base of bike shares and open up more transportation options to densely populated communities. Better access to public bike shares can make short commutes across a city, college campus, or a town center much faster and much easier. People who cannot make effective use of public transportation can use an automated bike share without needing to worry about returning or finding a bicycle. Global climate change is the greatest challenge of the 21st century. One of the greatest contributors to this is vehicle emissions, which grow exponentially worse in congested traffic environments. By increasing the convenience and utility of affordable bike share systems, Autocycle will reimagine sustainable transportation and increase bike share use. Replacing cars on the road with bike riders will reduce congestion and carbon-emitting vehicles, combating climate change.
We understand that our bike can't solve every problem perfectly. There will always be ways to modify and improve our research to make a bigger impact on society. But aside from what we previously discussed, we would like to suggest potential avenues that modifications of our original idea could tackle. For example, depending on how much weight our bike could handle, people with disabilities that restrict them from riding bikes or even using traditional methods of transportation could be pulled behind ours. Additionally, if the range of batteries is significantly improved, our bike sharing model could be implemented in areas that aren't completely urban. Overall, there is so much potential for doing good. The societal applications of our bike could tackle transportation issues, connectedness, climate change, and more. We hope that our research can move the world towards a brighter future.